Assalamu alaikum students. So today we are going to start our lecture 1 of our fluid mechanics 2 course, and as you know we will be covering the fluid mechanics 2 course from the same book that we studied for fluid mechanics 1, and that is the fundamental of fluid mechanics by Munson, and that is the 6th edition. In today's lecture we are going to go through some basic important concepts that we learned in fluid mechanics 1 course, and we are going to revise them because they will be needed in this course as well. So let's move on. So let's have a look at your course learning objective for your fluid mechanics 2 course first. And as you can see, CLO1 is related to pipe flows, and what we will do, we will apply appropriate equations and principles to problems related to viscous flow through pipes. So we will develop basic equations for our viscous flow through pipes, and we will apply those equations to pipe flow problems. This is related to your problem analysis PLO, that is PLO 2. The second CLO is to apply fundamental characteristics of boundary layer. You are already familiar with boundary layer, and what we will do, we will apply that boundary layer theorem to different flow and geometry conditions, and we will calculate our drag and lift forces. This is also mapped with the problem analysis PLO, that is PLO 2. And the third CLO is to analyze the selection of turbo machinery for a particular application. We will go through this in very detail because this is the major chunk of your FM2 course, and this CLO3 will cover your PLO3, which is the design part. That you will be selecting a turbo machinery for a particular application. So this is related to the design PLO, that is your PLO3. So now let's move on and revise some basic concepts that was related to your fluid mechanics 1 course. So the first concept that we covered in FM1 course was that we will treat our fluid, any fluid that is under our consideration, we will treat it as a continuum. And by continuum analysis, what we do, we take a certain volume of fluid. So instead of taking fluid and taking each and every particle of fluid, we take a first certain volume of fluid, and we try to develop basic equations for that fluid or that flow, and then we apply those equations to solve a certain problem. So this assumption makes our analysis a little bit easier, and these are the points that came after we assume that we will treat our fluid as a continuum. And the first one, as I discussed, is that we cannot study each and every molecule of fluid. So what we do, we take a certain volume of fluid, and for that volume we assume that the fluid properties are continuously changing, because that will be a certain volume. And what we can do, we can take average property of certain fluid properties, and we can actually use that. And also the fluid is uniformly dispersed, and this assumption is made to apply differential calculus for our problem analysis, and this continuum model allows us to use average properties of fluid within the volume it occupies. And for that purpose, we use this graph to explain that why we cannot study each and every every molecule of fluid, because if we go below a certain volume of fluid, we go into the microscopic region, and in that microscopic region the fluid properties are changing very abruptly, as you can see from this graph. And beyond a certain volume, we go into the macroscopic region, and in that macroscopic region the properties are changing, but they are not changing that abruptly. So for that purpose, we take the average of such properties, and then use these type of assumptions to develop our basic mathematical equations for any flow situation, and then apply those equations to solve a certain problem. So this was our first assumption that we made in our fluid mechanics 1 course, that we will treat our fluid as a continuum. So the first of the many properties that we studied, the first one was viscosity, and this is what we will be using in our FM2 course as well. And viscosity, as you remember, is the fluidity. It is the fluidity of a fluid, that how fluent a fluid can move if there is no resistance to the flow, and it is also known as the resistance to the flow. Resistance to the flow. You have already used that term quite a lot, and you are familiar with the example of water, that if a water flows, it will flow easily than honey or oil, because honey or oil is more viscous than water. We used this example to develop some equations for viscosity, and in this example you can see that there is a fixed plate right here, and there is a movable plate right here, and in between in between these two plates there is a certain volume of fluid. And what happens is we actually move this plate with by applying a force P, as you can already see. And by moving this plate, what happens is that if you take a fluid element right here, this vertical fluid element, and initially it is occupying this much space and it is vertical, but if we move this plate by applying a force P, what happens that this element will deform and this will come here, right here. And why it deforms like this is due to the no slip condition, that the fluid elements close to the boundary of this pipe actually sticks to this pipe, and this is called the no slip condition. This is the no slip condition that we used in our fluid mechanics 1 course. And by applying the no slip condition to this analysis, we develop a certain velocity profile like this, as you can see. This is the velocity profile that develops. Now, redrawing this velocity profile right here, we actually assign some points, point A, B, B dash, and actually this is delta beta, that is the angle, and this is the small delta A, the small distance that is displaced when we moved that movable plate by applying force P. So now let's apply some trigonometry to this triangle. What we came up with this is by applying the tangent delta beta, and tangent delta beta, by applying this tangent delta beta to this triangle, we come up with delta A, that is the small displacement that has occurred, divided by B, that is the width of this pipe or that fluid inside these in between these two plates. So this is our first analysis, and now what we are going to do, we are going to put a value of delta A, and delta A, as you can see, is a certain amount of distance, and by using V is equal to S by T, that is velocity is equal to displacement over time. So displacement can be equal to velocity into time. So this is what we are going to do. Sorry, I have to move that. This is what it is, as I already explained, and this is how it's going to look like when we put this delta A, that is the small displacement, is equal to velocity into a small increment in time, that is delta T. So this is how our equation, that is this equation, will now look like. So we will rearrange it a bit, and what we will call this is the actually this is the shear rate. This gamma dot right here is the shear rate, and that shear rate is equal to velocity over the width, and that is in turn equal to du, that is the change in velocity, divided by dy. So here this is this shows the gradient of the velocity. This shows the gradient of our velocity, and as you can see already from here, that the velocity gradient develops when we move in the y direction. Here the velocity gradient is developing, the u velocity gradient is developing when we move in the y direction. So that's why this is represented as du over dy. So this actually shows the velocity gradient. Moving further, what we have deduced from experimental work, we know that the shear stress is equal to the shear rate. This is we came up with this equation from experiments, and as we know that the shear rate is equal to this. So now the shear stress is directly proportional to the shear rate, and to remove this proportionality we will have to put in some value, and that value comes out to be our viscosity, that the shear stress is equal to the shear strain multiplied by the viscosity. So now we have our term viscosity, and this equation is true for Newtonian fluids. This equation is true for Newtonian fluids, and Newtonian fluids actually follow this equation, that the shear stress is equal to the shear strain, or the shear stress is directly proportional to the shear strain. So this is the equation that we will be using in our viscous flow of pipes when we analyze viscous flow in pipes. So you will have to keep that in mind. Now moving on. So then we started our fluid statics portion, and in fluid statics portion what we assumed is that our fluid will be at rest. So what can be the possible scenarios and the possible equations that we will have to develop to analyze a fluid in rest. So first of all, what we did, we came up with the concept of pressure, and pressure, as you already know, is the normal force per unit area. And then we came up with the Pascal's law, and Pascal's law deals with the pressure at a point. And as you already know that certain hydraulic systems are designed based on that law, and Pascal's law again deals with the pressure at a point. And what it states is that the pressure at a point in a fluid at rest is independent of a direction. So here it is important to note that a fluid must be at rest. And if a fluid is at rest, and if that fluid is applying a pressure on a certain point, so by changing the direction of pressure on the same point, there will be no effect, there will be no change in the magnitude of the pressure. Pressure will remain the same. So that's why the pressure is independent of a direction if it is applied in a fluid at rest at a certain point. What we did, we used this wedge-shaped fluid element. We applied F is equal to ma, and similarly if the fluid is at rest, there will be no acceleration, so this terms comes out to be 0. So we are left with this equation, that summation of all the forces is equal to 0. And then what we did, we actually summed all the forces that is applied on this fluid element, and at the end we saw that all the pressure forces, that is the PZ, PZ, Py, they are all equal. They are all equal. That is, at the end, this is what we were left with, that Ps is equal to Py is equal to Pz. So there was the pressure in the S direction, that is on the slant edge. Then the pressure on the Y direction, that is this pressure, and the pressure in the Z direction, they came all out to be equal, which satisfy the Pascal's law. So this was our first analysis that we did on a fluid element that was at rest, and we summed all the forces that were being applied on that fluid element, and then we came up with our Pascal's law, that is the pressure at a point in a fluid is independent of direction given that the fluid is at rest. So next we were concerned about the pressure variation in a fluid at rest. So what we did, we actually came up with the very interesting statement that for fluids or gases at rest, the pressure gradient in vertical direction at any point in the fluid depends only on the specific weight of the fluid at that point. So what does this statement means? If we take a certain tank, and in that tank there is a certain amount of fluid, so the pressure will only change in the vertical direction, and that pressure is dependent on the specific weight of the fluid, that is our gamma. So if we take this point P1, there will be a certain amount of pressure, and this pressure will be equal to the amount of fluid that is above that point and the specific weight of that certain amount of fluid that is above that point P1. So if we move us more in depth P2, so P2 will be greater than P1 because now there is much more fluid at point P2 above, and there will be too much specific weight acting on point 2. So the pressure will change in the vertical direction. If we take a tank and we move up and down, it will not change in this direction in the x or negative x direction, or in y or negative y direction, but it will only change in the z direction. So that's what we came up with. This is the equation, that the pressure gradient will not change in the x-axis, it will not change along the y-axis, it will only change along the z-axis, and here it is equal to minus gamma. Why minus gamma? Because as we move down in a certain fluid, the pressure actually increases. So this negative shows the negative sign because the direction is downwards, and this pressure is increasing as we move downwards in the negative z direction, as you can say, and this is the specific weight. So this is the equation that we came up with. This was very important, and we used it to solve different problems that were related to pressure at different points. As you can see from this figure, that here there is P1, here there is P2. So if we want to find pressure either at point 1 and point 2, so we can develop equations like this, that P1, now if I want to find a pressure at P1, then P1 will be equal to gamma h. Gamma is the specific weight and h is the amount of height that is up to point 2 or between point 1 and point 2 plus the pressure at point 2. So this is the basic equation that we developed by using different scenarios, and these are the same equations that were used when we were calculating pressure by using manometers. So this gives us a lot of equations. We were able to develop a lot of equations for different scenarios by using this analysis, and then similarly we can modify this equation to find our pressure head. This was also an important equation that we used to find our pressure head. So this was also the second part of our fluid statics, and we were concerned about the fluid at rest and how the pressure will change in a fluid if it is at rest, and we can now see that it changes in the vertical direction only or in the z-axis only. So after covering fluid statics, the basic phenomena of fluid statics, we came up with certain amount of pressures, and that two type of pressures was absolute pressure and gauge pressure. And what the equation tells us is that the absolute pressure is equal to the atmospheric pressure plus the gauge pressure, and basically these pressures can be differentiated by their reference points, and we use this figure to actually explain these two types of pressure. And what the absolute pressure was, that for absolute pressure the reference point was absolute zero. That means that it was the vacuum. So by measuring any pressure by taking the reference point as vacuum or zero pressure, and that pressure is called absolute pressure. And gauge pressure is the pressure for which the local atmospheric pressure is taken as the reference. So if you are taking atmospheric pressure as your reference point, as your starting point, and then you are measuring a certain amount of pressure above that atmospheric pressure, then that pressure will be known as the gauge pressure. And this is the formula to relate these three pressures, that is the absolute pressure is equal to atmospheric pressure plus gauge pressure. So now moving on to our next portion of our FM1 course, and that was fluid dynamics. We saw that what we covered, what were the basic concepts in fluid statics that we covered, and now we are going to see what are the basic topics that we covered in fluid dynamics. And in fluid dynamics, the first one was the Bernoulli equation. And as you know, when the fluid is flowing, by fluid dynamics, it means now that the fluid is flowing, it is in motion. So what will happen if we disrupt that motion, or we change the velocity of that fluid? So that can be possible in two scenarios: if we apply some pressure force, or if we change the position of that fluid, then it will alter the velocity of that fluid. So this is what the Bernoulli equations deals with. Bernoulli equations basically deals with the fluid motion, or you can also say that this is the equation of motion for fluids. So this is the Bernoulli equation that we derived along the streamline, and it is constant along the streamline, and it is equal to the pressure energy, the kinetic energy, and the potential energy. So any change in these two energies will result in a change in velocity or the kinetic energy of this any fluid, and this is what the Bernoulli equation deal with. And as you can say, the work done on a particle by all forces acting on the particle is equal to the change of kinetic energy of the particle. So any work done on a particle by all forces will result in change in kinetic energy of that particle. So work can be done by changing the pressure energy or the potential energy, and that will result in change in kinetic energy of a fluid or a particle of fluid. So Bernoulli equation can be written in terms of heights called heads. If we divide each of these terms, if we divide pressure by specific weight, if we divide this kinetic energy by specific weight, if we divide potential energy by specific weight, so we will get heads, Bernoulli equation in terms of heads. So this is now called the pressure head, this is the velocity head, and this is the elevation head is equal to constant along the streamline. So Bernoulli equation can be used for a number of applications, and what we saw that with the help of this setup we can find pressure in a moving fluid at any 2 points, at point 1 and point 2, and write an equation by using this equation. So we can write any equation by using Bernoulli equation and actually find pressures and velocity on any 2 points in a moving fluid. So for this scenario, what we did, we find the pressure, that is the total pressure P2. Here you can see that this is the pitot tube arrangement. If you remember, pitot tube is used to find the velocity of jets, and P2 right here is a point where we will measure the total pressure. P1 is the static pressure, and this term right here represents the dynamic pressure of the fluid. So as you can recall, this is the total pressure is equal to the static pressure plus the dynamic pressure. So this is also the term we defined by using this setup and using Bernoulli equation. Bernoulli equation was also used to measure flow rates in the flow rates measurement devices. And what we did, we took 2 points. Let's say if we remember this example, the example of Venturi, we would take 2 points, one before this opening and one after this opening, and we will apply Bernoulli equation on both of these points, and we will write equation for this flowing scenario, and we will actually be finding the pressure across these 2 points or the velocity, and ultimately with the help of flow rate equation AV, we would find the flow rate across this opening. So this is what we already derived using Bernoulli equation. So after fluid dynamics, what we did, we defined fluid kinematics, and fluid kinematics is dealing with how the fluid will flow. It is actually how will we describe that the fluid flows and how to describe fluid motion. And basically we described two descriptions for that, and one was the Lagrangian description. And Lagrangian description, in Lagrangian description, what we did, we would follow a single fluid particle, and we would see its properties with changing with respect to time only. And this is what this diagram represented, that actually we will take a fluid particle with reference to some position, that is the x, y, z axis, x, y, and z axis, and in Lagrangian description of motion follows a single fluid particle as it moves within the system. So by system we mean fluid, by system we mean fluid, and this is the description we are going to carry on, that by system we always meant fluid. And in that system of fluid we will tag one fluid particle, and we would follow that particle wherever it went, and we would calculate its different properties. Right now here it is shown that its velocity is being measured with respect to time. So this is one description, that was the Lagrangian description, that how we will define our fluid motion, and that fluid motion definition dependent on following a single fluid particle and measuring its properties with respect to time only. The other description was the Eularian description, and in Eularian description what we did, we would define a control volume within our system, and by defining a control volume we would actually fix the position of our control volume, and that control volume would be within the system, and now we will be studying only those fluid particles that would pass through this control volume, and by doing so we will actually defining different properties of fluid with respect to position and time. So the basic difference between these two descriptions was that in Lagrangian description we would be studying properties with respect to time only, and in Eularian description we would be studying properties with respect to position and time both. So this is what the basic difference was in these two descriptions of flow that we defined in our fluid kinematics. After defining our flow descriptions, that was the Eularian and the Lagrangian flow descriptions, what we did, we derived material derivative. And material derivative is basically this equation which helps us to find the local and convective change in a system of fluid for any property. For example, in this equation, if I'm going to find velocity, the change in velocity inside the system, so that change will be equal to the total change in velocity with respect to time will be equal to the local change. This is the local change, and that will be with respect to partial change in time, and that will be added on to the convective change. This is the convective change, and here, so basically what we are looking at right now is the total change in velocity is equal to the local change plus convective change, and local change is with respect to partial change with time, and convective change is with respect to the change in position of a fluid particle inside the system of a fluid. So we are with the help of material derivative, we are actually seeing the change in a fluid property with respect to time and position both, and we can generalize this equation and write it like this. There are some important operators, like here you can see that this is the total change, that's why it represented with the capital D, and this is the partial change, this is the V velocity that represents all the components of this velocity, the XYZ component of the velocities, and this is the del operator that contains all the partial terms, all the partial over partial X plus partial over partial Y plus partial over partial Z. So this is the del operator, and we will be seeing that too in our FM2 course. So this was the material derivative that that's main concern was to find the change in property with respect to time and position both. So after material derivative, what we did, we derived a Reynolds transport theorem, and Reynolds transport theorem deals with the extensive and intensive property of our system. And again, I'm going to repeat that by system we means our fluid. So extensive property depends on the amount of the system, means it depends on the mass, and it is normally represented with capital B. And by intensive property does not depend on the amount of system, and it is represented by B, and it is also written like this, that if we divide the extensive property by mass, it will give us the intensive property of the system. So this is what we first defined when we derived the Reynolds transport theorem. And what the Reynolds transport theorem do, it defines two entities. One is the control volume, which is the geometry, it is our geometry, and the other is the system, and by system again we mean fluid. So what Reynolds transport theorem does is it deals with the control volume and system, and when the system flows through the control volume, so it will tell us about the change inside the control volume in a system that is happening, and the change that happens when the system goes in and out of the control volume. So this is what the Reynolds transport theorem does. Looking at its equation, you can see that the total change in the extensive property of a system with respect to the time is equal to, this is the total change in the system, in the extensive property of a system with respect to time is equal to the change within the control volume, that is the partial or partial t, that is the local change inside the control volume, plus the stuff that crosses the boundary, means that the change in the extensive property of the system when it goes in and out of the controlled volume. This can be further generalized and written in like this. So this is the total change in the extensive property of the system and equal to the partial change inside the control volume of the extensive property inside the control volume, and this is the change when the system goes in and out, means at the control surfaces. By control surfaces we means the by control surface it was meant the inlet and outlet of the control volume through which the system will flow. So this term right here deals with the inlet and outlet of the control volume, and the change in the system that happens when it flows through the inlet and outlet of the control volume. This deals with the change inside the control volume, and this is the total change variable, which is equal to this. So Reynolds transport theorem was very important for us because using this extensive property parameter, we can now use our conservation of mass by taking our extensive property as mass, by taking our extensive property as momentum, by taking our extensive property as moment of that momentum, and by taking the extensive property as our energy. So this gives us our continuity equation. This gives us the change in momentum that occurs due to the change in force. It actually enabled us to also take into account the forces that are actually applied on the system or the control volume, and this helped us to find the torques that are actually being applied by the system or on the system using turbine or pump. And this right here gives us our energy equation that we use to find our energies that are required to run a certain pump, or the energy that we can extract from a certain turbine. So this was very important for us, and we use that for different conservation principles that we are going to see in the next slides. So after the deriving Reynolds transport theorem and seeing its applications, what we did, we actually defined a finite control volume, and we did the Reynolds transport theorem analysis on that, and that was called the Reynolds finite control volume analysis. And as you can see, this again represents the left hand side of our Reynolds transport theorem, and here now as you can see, the extensive property right here is the mass of the system. So this was the first part of our finite control volume analysis, in which we saw the conservation of mass, and by putting mass in terms of density, that is density is mass per unit volume. So here mass was taken as density into volume, and here everywhere in Reynolds transport theorem we substituted that for mass. So now this is our Reynolds transport theorem for conservation of mass principle, and by taking this term right here as if we take that our flow is steady, and by steady we means that there is no change with respect to time whatsoever in the properties, and by taking the flow steady we take all the terms which represents the change in time as 0, and we were just left with this term. So this term was also turned into 0, and we were just left with the change at the control surfaces. So by taking mass as our extensive property, we derived our A1 continuity equation, A2 V2. So this was our continuity equation that we derived by taking mass as our extensive property and putting it in the Reynolds transport theorem and assuming the flow to be a steady flow. So this is what we did, and then we also saw the application of this equation for a certain number of scenarios. In the first scenario, our control volume was fixed and it was non-deforming. So this was exactly what I already mentioned, that it was non-deforming, the control volume was fixed, so there was no change in the extensive property of the system inside the control volume, so these terms were neglected. This was the first scenario. In the second scenario, our control volume was moving, but it was not deforming. So here we saw that the concept of absolute velocity and relative velocity, but again it was related to conservation of mass principle. Then the third was the deforming control volume. As you can remember, we saw a syringe in that case, and we took as a deforming control volume. So in that case, the change inside the control volume was not zero. So this is what the Reynolds transport theorem in terms of mass conservation was. In the next part, what we did, we took the extensive property, that is the B as our momentum. So by applying Newton's second law and linear momentum on the Reynolds transport theorem, what we did, let's go through the Newton's second law first. That the Newton's second law of motion for a system is the time rate of change of linear momentum of the system is equal to sum of the external forces acting on the system. So this is what we derived our Reynolds transport theorem down to by taking our extensive property as momentum, and again here representing mass as our, in terms of density and volume, and putting it in the Reynolds transport theorem. So this is what this statement represents, that the time rate of change of linear momentum, this right here is the linear momentum, and this is equal to the sum of the external forces. So now with the help of this equation, we can also take into account the forces that are actually acting on our system or the control volume. This is how it was represented in the Reynolds transport theorem, as you can now see. And this is what the Reynolds transport theorem for conservation of momentum looked like. And this right here represents again the change in the momentum of the system, which was equal to the change in momentum inside the control volume and the change in momentum at the control surfaces. And this is what this statement actually represents, this equation. This right here is the time rate of change of linear momentum of the system, which was equal to the time rate of change of linear momentum of contents of the control volume plus the net rate of flow of linear momentum through the control surfaces. And to simplify it a little bit more, this is what it looked like. Actually, on the right hand side here, we get the summation of forces that will occur by the change in system inside the control volume and the change at the control surfaces. So now we can also take the forces into account that are being applied on the control volume or on the system, that is our fluid. So next, after momentum, what we did, we derived the moment of momentum equation by using the Reynolds transport theorem, and this is again the Reynolds transport theorem for the momentum equation for the Reynolds transport theorem. And here you can see that our extensive property is again momentum, but if we take the moment of this momentum by multiplying it with a certain amount of momentum right here, by multiplying these momentums by momentum, so what it does, it gives us the torques. It gives us the torques, and torque is an important parameter when we are talking about the pumps and turbines. We are actually interested in the torques, and torque is actually the energy that is required to turn us to give rotation to a certain rotational object or a certain shaft. So this is what torque is used for, and this equation right here represents the time rate of change of momentum of the system, the total change with respect to time in the moment of momentum, and that is equal to again time rate of change of momentum of the contents of the controlled volume plus the net rate of flow of momentum through the controlled surfaces. So this equation right here was used to to find torques in case of pumps and turbines. So next what we did, we used the first law of thermodynamics to derive our energy equation, because at the end we were more concerned about the energy requirements for using a certain type of machinery like pump, and what will be the energy output if we use a turbine. So, and finding the efficiency of such machines. So this is what we did. We used the first law of thermodynamics, and what we did now, we took the extensive property of our system as energy. The first law of thermodynamics deals with the conservation of energy principle, and this actually gives us that how much energy is required to run a device and how much energy can be extracted from a device. So to run a device, it is basically how much energy is required to run a let's suppose if we are using a pump, so how much energy can be given to a certain amount of system by using a pump, or if you are using a turbine, so how much energy can be extracted from our system to run a turbine. So these are the basic two devices that we talked about. And moving on, by putting our extensive property as our energy, what we did, we saw the total change in energy with respect to time, and that energy was equal to the change in the internal energy of the system plus the work that was done on the system, or the work in and out of the system. By work in, we means that work is done by the system, and by w dot out means work out means that the work is done by the system on a certain control volume or a certain object like a pump and turbine type of thing. So what the total energy was equal to, it was equal to the internal energy plus the kinetic energy plus the potential energy, and these are the terms that we use to represent the different types of energy. And then we actually divide these three types of energy by their mass, so that gives us the specific energies, the specific internal energy, the specific kinetic energy, and the specific potential energy. And then we substitute these values inside the Reynolds transport theorem to get the total change in the energy of a system with respect to time is equal to the change in energy inside the control at the control surfaces, the change in energy that occurs at the control surface at the inlets and the outlets, and the change inside the control volume. Further, this can be derived, this equation can be further derived into the energy equation that we used to find different type of efficiencies and energy requirements and energy outputs of our different type of pumps and turbines. And from here we actually defined rate of work transfer, that how work transfer will take place. So work transfer can be with the help of a shaft, that if we do work on the shaft, or work is done by the shaft on the fluid, then the normal work done is actually the forces that are there at the inputs and the outputs. So to overcome these forces, work has to be done, and the work that has to be done to overcome the viscous forces, the viscosity of the fluid. By shaft work, we means that the if a pump does a work on the fluid, so it is actually adding energy to that fluid, so that's why that work is positive. And if we take the shaft of a turbine, so in that case the fluid is working doing work on the shaft, so in that case it is losing energy, so that's why the negative sign is here to represent the energy extraction from the fluid. And then this was our final form of our energy equation, that is the change inside the control volume, that is the change across the control surfaces, the change in energy across the control surfaces at the inlet and the outlet, and here is the total change, which represents the change due to the internal energy and the change due to the work done on the shaft or by the shaft, and this gives us at the end the energy equation. So these were the basic concepts that we covered in our FM1 course, and after that we also covered our differential analysis and our dimensional analysis, but we will cover those topics along as we move along in our FM2 course. So this was for your revision to revise you with the basic and remind you of the basic concepts that were used in our FM1 course.